Storing quantum information in three-level atomic systems interacting with a single radiation field is made possible through a novel method. By performing simple local SU rotations on the Hamiltonian, one atomic level is decoupled from the electromagnetic field under equal detuning for both Lambda and V configurations. This transformation yields two effective two-level systems, or qubits, plus an isolated atomic level, enabling information exchange between the qubits. Crucially, this approach preserves the quantum phase diagram of the system, making it suitable for quantum information storage, retrieval, or communication. Building upon established models like the Rabi and Dicke models, this method generalizes the interaction to a finite number of atoms, offering a significant advancement in quantum information processing. The storage of quantum information in a generalized Dicke model is discussed via a simple rotation. Previous efforts to solve the model analytically, including adiabatic elimination procedures in various configurations, are highlighted. The paper focuses on a specific model with three-level atoms interacting with a single mode of an electromagnetic field, exploring the mathematical structure in three atomic configurations. SU local rotations decouple the M-dipolar interaction between two atomic levels, leading to an effective Hamiltonian. The quantum phase diagram and its invariance under certain unitary transformations are also discussed. The paper is organized into sections establishing the generalized Dicke model, presenting the SU structure, and providing expectation values of atomic energy levels. In the generalized Dicke model, a system of Na atoms interacts dipolarly with a single mode of electromagnetic field, governed by a Hamiltonian that depends on control parameters such as photon frequency, atomic energy levels, and dipolar strengths. The field and matter operators, obeying the SU algebra, are defined, with the field mode frequency set to match the atomic energy level separation. The dipolar interaction is characterized by forbidden dipolar transitions, which arise from the parity-conserving Hamiltonian. This Hamiltonian preserves the parity of the number of excitations, ensuring that transitions between states with even and odd numbers of excitations are forbidden. The detuning for transitions, defined as the energy difference between the field mode frequency and the atomic energy level separation, plays a crucial role in determining the system's behavior. By introducing these key elements, the generalized Dicke model provides a framework for understanding the complex interactions between light and matter, with implications for quantum information processing and many-body physics. In this section, we explore the effect of simple rotations on the system to obtain new Hamiltonians. By applying specific rotations, we can eliminate the interaction between certain pairs of levels and the EM field, effectively reducing the system to an isolated atomic level and a two-level Dicke model. This is achieved through the use of SU groups constructed from SU generators, particularly by adding missing generators to complete an SU algebra. A key concept is the rotation through the third element of the corresponding SU subalgebra, which enables the elimination of specific interactions. The transformed Hamiltonian is derived, showing the reduction of the system's complexity while maintaining its essential features. In the realm of quantum information storage, a generalized Dicke model is proposed, leveraging a simple rotation to store quantum information. This model comprises three atomic levels and an electromagnetic field, with specific interactions between them. By applying a rotation, the Hamiltonian for this system can be simplified, removing one of the atom field interactions and yielding a new matter-one body coupling between atomic levels without dipolar transitions. The parameters of the simplified Hamiltonian, as outlined in Table 2, depend on the choice of rotation angle alpha. Depending on the configuration, either the Lambda or V configuration, the one-body matter interaction term, lambda jk, can vanish when the atomic levels are degenerate, effectively reducing the three-level Dicke model to an effective two-level Dicke model plus an isolated atomic level. Notably, this equal detuning case is independent of the field frequency in the cavity. The proposed procedure for storing and retrieving information, or exchanging information between qubits, involves performing rotations that isolate specific atomic levels. For instance, in the lambda configuration, applying the rotation U12, arctan, micro 13, micro 23, isolates level omega 1, leaving a qubit formed by levels omega-2 rightwards harpoon over leftwards harpoon omega-3 with a null population expectation value for level omega-1. Subsequent rotations can then be used to switch to a state where level omega-2 is decoupled, resulting in a qubit formed by omega-1 rightwards harpoon over leftwards harpoon omega-3, and the population expectation value A22 of level omega-2 vanishes. This process demonstrates a method for controlling the interactions between atomic levels and the electromagnetic field, potentially enabling the storage and retrieval of quantum information within the generalized Dicke model. In the context of a generalized Dicke model, this page discusses the process of storing quantum information through a simple rotation. The figure illustrates rotations carried out on a three-level Dicke Hamiltonian coupled with a one-mode electromagnetic field in Xi, Lambda, and V configurations. These rotations aim to eliminate the electromagnetic coupling between the atomic level states, facilitating the exchange of information between two qubits. The fidelity between the two qubits is exactly 1, indicating perfect information transfer. In the context of quantum computing, a novel approach has been proposed for the storage and retrieval of qubits in a three-level Dicke model. This method begins with an eigenstate of the Hamiltonian h lambda, followed by a rotation U12, arctan, micro 13, micro 23, to store information. The retrieval process involves another rotation, U12 minus arctan, micro 23, micro 13, which utilizes the population in the atomic level omega-2 as a classical bit. This dynamic process is characterized by quantum Rabi oscillations between levels omega-2 and omega-3, and then switching to omega-1 and omega-3. These rotations effectively reduce the three-level Dicke model to an effective two-level Dicke model plus an isolated atomic level, thus facilitating the storage and retrieval of qubits. To assess the robustness of this result, non-degenerate atomic levels were considered. The expectation value of population for each atomic level under these rotations was calculated. Notably, the population of the isolated level was found to be extremely small, even with a 20% detuning difference, ensuring high fidelity between the stored and retrieved states. This approach presents a promising strategy for enhancing the efficiency and reliability of quantum information storage and retrieval processes. In the context of storing quantum information in a generalized Dicke model, a simple rotation is employed to facilitate the process. The expectation values for the population of atomic levels omega-1, omega-2, and omega-3 are illustrated in Figure 2, both during the storing stage and the retrieving stage, with parameters omega-1 equals omega-2 equals 0, omega-3 equals 1, omega equals 1, and Na equals 4. The effect of the one-body matter interaction term on the isolated atomic level is examined, revealing similar results for both configurations through numerical diagonalization of the Hamiltonians. In the atomic V configuration, the Hamiltonian without rotations, HVI, is given by equation 1, with micro 23 equals 0, prohibiting the transition omega-2 rightwards harpoon over leftwards harpoon omega-3. Under the considered rotations, the Hamiltonian takes the form of equations 9 and 10, where the atomic populations of the ground state are shown as a function of the control parameters micro 12 and micro 13 for a single atom Na equals 1 in Figure 3. The population of the atomic level omega-1 remains close to unity in the normal region, decreasing to A11. Approximately equals 0.5 in the collective region, indicating the significant contribution of other atomic levels to the ground state. The figure also displays the corresponding atomic populations for the transformed Hamiltonians, equations 9 and 10, respectively. Notably, the atomic population of level omega-1 remains unaltered, while those of the higher atomic levels undergo a drastic change, with the higher atomic level populations exchanging their roles under these rotations. The expectation value all of the atomic population of the atomic level that decouples after the rotation remains close to 0, with a deviation of less than 0.05% in the atomic population of this decoupled state, even with a 20% detuning in the atomic level, demonstrating the robustness of this property of the rotations. The storage of quantum information in a generalized Dicke model can be achieved through a simple rotation. For a single atom in the V configuration, The expectation values of atomic populations are functions of control parameters. Ground states of different Hamiltonians are analyzed, revealing that the population of uncoupled levels is nearly zero. A phase diagram is introduced to characterize abrupt changes in the ground state using fidelity between neighboring ground states. This method can also be applied to excited quantum states to determine quantum phase transitions. The section concludes by mentioning the application of this procedure to a system with two control parameters, illustrating its potential for studying quantum phase transitions in excited states. The authors discuss the storage of quantum information in a generalized Dicke model via simple rotations. They calculate the fidelity between neighboring states, fraught, micro plus delta micro, along lines based at the origin, considering the step size delta micro greater than 0. The fidelity is approximated using equation 12, involving the operator k, defined differently for the Xi, Lambda, and V configurations. The results of the calculation of d alpha, d micro, necessary for equation 12, are presented in Table 3, showing derivatives for each configuration when one coupling strength is fixed while the other varies. The phase diagram is found to be invariant under SU, 2, rotations, even when these depend on the control parameters, as shown in Appendix B. Despite differences in fidelity values between neighboring states, the stability and equilibrium properties are preserved for the original and rotated Hamiltonians, as illustrated in Figures 46. The calculation of fidelity along lines maintaining one coupling strength constant does not always detect all minima, but along linear and/or quadratic functions passing through the origin, all minima are determined. Figure 4 presents the phase diagram, given by the minimum of the fidelity between neighboring states, in the Xi configuration, for the ground state of Hamiltonian 6, in both resonant and non-resonant cases, with varying numbers of atoms Na. The results are compared with the separatrix obtained from the variational solution using coherent states as test functions, which has the analytical expression given by equation 13. The authors examine the storage of quantum information in a generalized Dicke model via a simple rotation. In the Xi configuration, the separatrix for atoms is presented in Figure 4 as a function of the number of atoms, Na, comparing the quantum separatrix with the corresponding variational solution. The parameters used are omega-1 equals 0, omega-3 equals 2 for the atomic levels, and omega equals 1 for the field frequency. Two cases are considered: equal detuning with omega-2 equals 1 and different detuning with omega-2 equals 1.5. The quantum separatrix converges to the variational one as Na increases, with the variational separatrix remaining fixed for any Na. The factor of 2 that multiplies the dipolar strength μjk arises from the absence of the RWA approximation. In the normal region, the quantum ground state is characterized by states close to both the vacuum field contribution and the matter ground state, resulting in the variational separatrix lying near the quantum calculation around the μ23 axis. The effect of considering a different value of detuning is to augment the normal region, as seen by comparing the regions limited by the variational separatrix in Figures 4a and 4b. The separatrix for this atomic configuration has the same shape independently of the detuning values, as described by equation 3. In the atomic V configuration, the separatrices are shown in Figure 5 for Na equals 1, 2, 3, and 4 atoms, with zero detuning in Figure 5a, and non-zero detuning in Figure 5b. The variational separatrix in this case obeys equation 14, which reduces to a circumference for equal detuning and has an elliptic shape for different detunings. The research proposes a novel methodology for retrieving quantum information through a simple rotation to the Hamiltonian in atomic systems interacting dipolarly with a one-mode radiation field. The atomic V configuration is considered, where population of certain states reaches up to 0.05% with a detuning of 20%. As resonance is approached, symmetry arguments suggest high fidelity between the retrieved and initial photon states. The quantum separatrix for atoms in the atomic V configuration is examined as a function of the number of atoms, comparing it with the corresponding variational solution. It is observed that as the number of atoms increases, the quantum separatrix tends towards the variational one, both for equal and different detuning conditions. The atomic lambda configuration is also studied, where the variational separatrix is given by a specific equation involving the detuning and the dipolar coupling strength. The shape of this separatrix is that of a circumference for equal detuning, and it imitates the shape of the atomic sheet configuration for different detuning. This research presents a new approach to retrieving quantum information, demonstrating its feasibility in various atomic configurations under different detuning conditions. The storage of quantum information in a generalized Dicke model is discussed using a simple rotation. A figure compares the separatrix for atoms in the lambda configuration with different numbers of atoms, illustrating the approach to the variational solution as the number of atoms increases. The method enables the obtention of the full energy spectrum of the system, which is written in bands associated with the number of particles. Parity symmetry is used to reduce the dimension of the space under study, effectively freezing one of the three atomic levels and reducing it to a two-level Dicke system. This approach is supported by DGAPAUNAM under Project Indiana 100323. The authors explore the storage of quantum information in a generalized Dicke model via a simple rotation. They focus on the rotation of the three-level Dicke Hamiltonian with one electromagnetic mode for arbitrary alpha. The rotation operator, denoted as UJK, alpha, is defined using the SU relevant groups for each three-level atomic configuration. Specifically, the operator KJK is introduced, which is a combination of the latter operators AJK and AKJ. The rotation UJK, alpha, is then defined as the exponential of alpha KJK. The authors derive the transformed operators ALM, J, K, by applying the rotation UJK, alpha, to the original operators ALM. They use a well-known method, which involves finding a differential equation for each operator. The first derivative yields a coupled system of equations, and taking the second derivative leads to a second-order differential equation for each generator of the SU algebra. The transformed operators are then expressed in terms of the original ones, with at least one coincidental index with the transformation. The resulting expressions for AJ, AK, AKJ, AJM, ACM, ALJ, and ALK are presented. These transformations are valid for an n-dimensional algebra. The authors highlight the significance of this special rotation, which is defined by the forbidden atomic transition for each atomic configuration. For instance, the rotation U31, alpha, corresponds to the Xi configuration, U12, alpha, to the lambda configuration, and U32, alpha, to the V configuration. The advantage of this rotation lies in the ability to eliminate one term of the matter-field interaction in the three-level Dicke model with a single electromagnetic mode, for an appropriate value of alpha. In the generalized Dicke model, storing quantum information relies on a Hamiltonian that incorporates atoms in the Xi configuration. This Hamiltonian consists of multiple terms, including one body-matter interaction and dipolar transitions. To adapt this framework to the Lambda and V configurations, transformations are applied, which eliminate specific dipolar transitions under certain conditions. A key parameter, alpha, plays a crucial role in these transformations, enabling the elimination of particular transitions and simplifying the Hamiltonian. Notably, in specific configurations, such as atoms with degenerate ground states, one-body interaction terms are naturally eliminated. This highlights the intricate relationships between the various terms in the Hamiltonian and the underlying atomic configurations. Through a series of mathematical derivations, the authors demonstrate the feasibility of this approach, showcasing the complex interplay between the different components of the Hamiltonian. The resulting expressions underscore the nuance and richness of the generalized Dicke model, providing a foundation for further exploration of quantum information storage. In the context of a generalized Dicke model, the fidelity between two neighboring states can be calculated using a simple rotation. This process involves an infinitesimal unitary transformation U, which is a function of parameter micro and its impact on the overlap between states psi, micro, and psi, micro plus delta micro. By expanding U, micro plus delta micro, up to second order in delta micro, we derive an expression for the squared absolute value of the overlap, fraud, in terms of the state overlap and the expectation values of k and k2, where k is an anti-Hermitian operator. Assuming that the state overlap and expectation values are real numbers simplifies this expression, leading to a more tractable form for fraught. This simplified expression depends on the first and second derivatives of u with respect to micro. In our specific case, the minima of this simplified expression are identical to those of the original expression, validating the approximation. This analysis contributes to understanding how quantum information can be stored in a generalized Dicke model using a simple rotation. It provides insight into the stability and coherence of quantum information under such transformations, which is crucial for assessing the feasibility of the proposed method for quantum information storage and its potential applications in quantum computing and other quantum technologies. The paper explores the concept of storing quantum information in a generalized Dicke model through a simple rotation. It begins by discussing the original Hamiltonian, which remains invariant for two special rotations considered. The paper then delves into various aspects of this model, including its potential applications and limitations. In the generalized Dicke model, quantum information is stored in the form of collective spin states of an ensemble of two-level atoms. These atoms are coupled to a single mode of a quantist electromagnetic field, resulting in a complex interplay between the atomic and photonic degrees of freedom. The Hamiltonian of this system is given by the sum of three terms: the atomic energy, the photonic energy, and the interaction term representing the coupling between the atoms and the photons. The authors considered two special rotations, R1 and R2, which leave the Hamiltonian invariant. These rotations are defined as combinations of rotations around the x, y, and z axes of the block sphere, and they play a crucial role in understanding the properties of the generalized Dicke model. The paper also discusses the concept of quantum error correction, which is essential for any practical implementation of quantum information storage. The authors propose a scheme based on the surface code, where logical qubits are encoded into a larger number of physical qubits, allowing for error detection and correction. However, the paper also highlights several challenges and limitations associated with the generalized Dicke model. For instance, the model requires precise control over the coupling strengths between the atoms and the photons, as well as the ability to maintain coherence over long periods of time. Additionally, the model is sensitive to decoherence and dissipation, which can lead to loss of quantum information. In conclusion, the paper presents a novel approach to storing quantum information using a generalized Dicke model with simple rotations. While the concept holds promise, it also faces several technical challenges that need to be addressed for practical implementation.